Solutions and calculations regarding solutions are not new and are taught in high school chemistry classes right through to university. However, many small-scale miners and or prospectors may have forgotten some of that knowledge, and others may have not taken any formal chemistry courses. Bottles of acids and other solutions will need to be diluted at times. For those that are attempting or are considering doing your own collection and refinements of those noble and precious metals, you may find that this presentation is worth noting. I am Rob Boyko, Boyko Mineral Exploration. Before I get into the subject, there are a few definitions that I need to clarify. First is the term mole. It is abstract. It is given to anything or represents anything. Its symbol is a lowercase n. For example, the atomic weight of gold is 197 grams. It can then be said that 1 mole of gold equals 197 grams, or 197 grams equals 1 mole of gold. The small or lowercase c simply stands for concentration. In solutions chemistry, it represents a concentration of a solute in a solution. For example, hydrochloric acid would be the solute, and the added water to the mix is the combined solution. The lowercase c represents the concentration of the hydrochloric acid that is in the solution. The uppercase M stands for molarity, and without going into a lot of detail, consider it as C, or the concentration of a solution. It is also used to describe the molecular weight. This would be the atomic weight of a molecule. V simply stands for volume and is usually presented in the form of liters or milliliters. WW simply denotes a weight-to-weight ratio and is normally presented as a percentage. VV, same as WW, denotes a volume-to-volume ratio and is also presented as a percentage. AT, WT, stands for atomic weight of an atom or element. And the capital MWT stands for molecular weight of a molecule. The tools that will be needed will be a graduated cylinder for more precise measurements, but in most cases graduated beakers as the one shown will be sufficient. A set comprising of various sizes up to 1 liter is recommended. Most acids come in large volume sizes when purchased. You will also need a calculator, as will be shown in this presentation, and a notebook with a pencil and eraser will be required as well. This is one of the most important tools in my toolbox, the periodic table. This slide shows the table that I use. These tables can be downloaded from the net free of charge. Just do a Google search and download one for yourself. The most relevant part of this table when it comes to solutions is the atomic mass. Notice nickel, which has a symbol Ni. It has an atomic weight of 58.7. Because this is a mass, the 58.7 is in grams. Therefore, 1 mole of nickel has an atomic weight of 58.7 grams. In your notebook, you would write it as Ni AT.WT.58.7. This table will be used throughout this presentation. Chemistry textbooks and chem instructors will start talking about what a concentration is. Then they will give you this formula for molar concentration. This is a classic example of how it applies. Using 20 grams of salt and dissolving it into 1 liter of water. Notice that I said 1 liter. I could have said 500 milliliters. However, the volume in this formula stipulates liters, and therefore the milliliters would have to be converted to liters. Using a volume of 1 liter is just for convenience in this example. First, the molecular weight of the sodium chloride molecule will need to be known. Using the periodic table and looking up the individual elements and adding up the atomic weights gives us the atomic weight of 58.5 grams of one molecule, that is mole, of sodium chloride. Using the formula, the 20 grams of salt divided by the molar weight gives us the concentration of 0.34 moles per liter. This would open the door for further discussion, but at this point, we're not interested in molar concentration. So let's continue. Most solutions will have their containers labeled showing the concentration of the solution. The label may show the molarity of the solution as in the previous slide, or it may be in the form of either weight to weight, volume to volume, or weight to volume in percentage. The weight to weight percentage, usually but not always, refers to the weight of solid material. The formula is the same for all formats. The salt example shows the weights of salt mixed with sand, a mix that may be used in the winter for sanding roads. Solutions are always made up of solute, in this example, the salt, and the solvent, which in essence would be the sand, which makes up the solution or mixture of the combined ingredients. The same is true for the volume example. In this instance, we are calculating the percent concentration in volume of solute to solution. In this example, the result would be read as 33.3% hydrochloric acid per volume of solution. This volume could be 1.0 liters or it may be 500 milliliters. As with the 1 liter bottle being used up, the concentration would be the same. The percent weight of solute in the volume of solvent is not relevant in this discussion, and therefore will not be discussed, as it has other applications beyond the scope of this presentation. If you have taken any chemistry courses, you will be familiar with this formula. At first, as it is presented, is a little confusing. Mathematically, one concentration cannot be equal to the other concentration unless the two solutions are of the same type and concentration. It is a lot easier to think a little abstract and say that one concentration after dilution will be the second concentration. When applying this methodology, all values must be in the same value. If V1, that is volume 1, is in milliliters, then V2 must be in milliliters, and so on. It is best to rewrite the equation as shown for some clarity as to what you want to do. The equation shown calculates the required amount of distilled water to be added to 500 ml of acid, having a concentration of 68% volume, in order to dilute the acid to a stock concentration of 20% volume. If you needed to increase the concentration, then the water would have to be evaporated, and the equation would be flipped. It is much easier to dilute than concentrate. In every instance, small-scaled miners and prospectors, dilution will be required, and therefore the discussion on increasing concentration will not be discussed. The calculation shows that 1,700 milliliters of water will be required making up the solution. Since we already have 500 milliliters to start with, it is subtracted from the 1,700 milliliters. The amount required for the dilution will be 1,200 milliliters of distilled water. Mostly, acid labels will show concentration as volume, but occasionally there are times when a label will show the concentration as weight. This also applies to procedures. You may read in an instruction manual to add 20% sulfuric acid weight to weight. You take down a bottle of concentrated acid of, let's say, 35% volume as stated on the label. Now what? You have to convert from volume to weight. And this is not only tricky, but can be complex. The better way, in my opinion, is to convert both what you have and what you want to a molar concentration and then dilute it. Mass, in this case, equals density. In order to complete the calculations, a density table will be required. An example is shown. I find it very difficult to obtain a free copy of a complete set of tables on the net. However, a good source to bookmark is a website titled The Engineering Toolbox. That would be theengineeringtoolbox.com. It has been my go-to resource for density information, and have started to create my own table of densities. Tables are important as densities of acids will vary with temperature. Temperature is not shown in this table. This table shown is only an example. Going forward, in the next few slides, will be an example of converting for the purpose of diluting to the required concentration. You now know that the term WW refers to the grams of solute per grams of solution, and that the percentage specifies the concentration of the solute in regards to the total solution. In all respects, this is mass or density. The phrase or statement that you may find in some textbooks or other documents will be written as the concentration, which is moles per liter, is equal to the solution's density, designated P, divided by the molar weight of a substance times mx. Confusing? It is. This is what it refers to in practice. The percentage of the solution multiplied by the molar weight of a substance, then multiplied by the solution's density, will equal the concentration of the solute in moles per liter. Now, based on the 35% volume-to-volume stock solution of 500 milliliters, which is needed to be diluted to 20% weight, to reach that 20% weight, based on the equation, 20% being 0.20 grams, divided by the molar weight of the acid of 36.5 grams per mole, multiplied by the density of the acid, which is 1.8 grams per milliliter, will equal 9.86 moles per liter. Now we have the molar concentration of the hydrochloric acid that is wanted. You also know now that the term VV refers to the amount of solute in respect to the amount of total solution. This also needs to be converted to moles per liter or simply molar concentration. In practice, the equation is almost the same as used for the weight conversion. The percentage of 0.35 divided by the mole weight of the acid, then multiplied by the acid's density, and then divided by the total volume of the solution, equates to the molar weight of the solution that you have in moles per liter. In this case, it is 34.52 moles per liter. We now have the required information for the dilution of the acid equal to 20% weight to weight. We know that the stock solution is 35% volume to volume, which is equal to 34.52 moles per liter. To make this simple, we will use the entire 500 milliliters to form a stock solution equal to 20% weight to weight. Using the formula C1V1, C2V2, and rearranging the values as shown, the equation of C1V1 divided by C2 is used. In order to have a solution of 20% weight to weight, the total solution would have to be 1.75 liters. Since we are starting with a half a liter, the amount of water that would be required will be 1.25 liters. Now, using a proper vessel or container, 1.25 liters of water would be added, followed by the 500 milliliters of stock solution, and mixed thoroughly. This would give us the required acid with a concentration of 20% weight to weight. Remember that the concentration of a solution will stay the same, if not diluted or concentrated. Therefore, 20 mils of the solution from the 500 mils of solution would have the same concentration. Also, C1V1 equals C2V2 can be flipped. This would be represented as C2V2 equals C1V1. The amount of water that would be needed to be added for dilution can be easily determined by converting what you have and what you want to molar concentration. In my opinion, is much easier and easier to understand. This was a quick, practical presentation on converting acid concentration values in reference to what you have and what you want for the purpose of diluting your acids for analysis of your ore material and or concentrates. This video edited presentation was presented due to a question from an individual who stumbled on me while working in the field. He told me that he was a student and asked if he could help or just observe. I asked him to dilute some acid for me and he looked a little confused, so I stopped what I was doing and gave him a quick on-the-job lesson, so to speak. I decided to add this presentation as I realized that this topic or discussion is not presented to students that often and mostly neglected. If you like this presentation or know of someone who may benefit from this information, please give it a like, a thumbs up, and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.